Okay, so for my project, I wanted to talk about harmonic oscillations and their relationship with differential equations. So in the simplest system, we have a mass attached to a wall by a spring on a frictionless surface, and thanks to Newton's second law, F is equal to ma. And this, considering this is the sum of any force pair is equal to 0, which I think is third law. We can set the F net is equal to 0 because there's no new force being added to it once we start the start the oscillation, excuse me, and we're left with ma minus kx, or ma minus kx is equal, or plus kx is equal to 0, excuse me. It's supposed to be ma is equal to negative kx, because our initial force we're given is equal to all that the spring can store, which makes sense. So if we we set this as a differential equation, we can find that, and we use this term omega, which describes the angular frequency, is equal to k over m. We'll then see that the solution to this differential equation at first glance is equal to plus or minus I omega t. And this can be expressed as a sine and cosine function, which I will do later on, but I just want to talk about a different system first. So this next system is a little more complicated. You're dealing with two masses on a frictionless surface attached by a spring with spring constant k. And so you have your equilibrium length of the spring, which is r naught. Then you have your displacement, x1. And since it's a symmetrical system, each side is displaced the same amount. So here it's just, we just assign negative and positive values here to make direction easier. So we make this side positive and this side negative. You'll have x1 minus negative x2 when you're equal to, which gives you the total different distance and makes things easier. And here you have the negative. The negatives work together to give you just a negative version, because the force here is moving this direction. The forces are opposite on each side. So the mass and acceleration are traveling this way initially, and the spring is pushing outwards because it is being compressed. So again, if we just solve for the system, we'll, excuse me, if we don't solve, if we abbreviate these as x because it's easier to write, and then subtract m1 from m2, or x1 from x2, after dividing by the respective masses, we're left with this equation, which is x2 double prime minus x1 double prime is equal to k over 1 over k times the quantity 1 over m1 plus 1 over m2 times x. So now let's consider this, that let's take a look at what does this expression mean. So this is equal to 1 over the center of mass. So the center of mass refers to the location between these two bodies, which is the respective center of mass of the system. So it's kind of like the average. It's like the average mass of the system. And because everything's equidistant, it's just the center of the system. But you can, even if it wasn't the center of the system, you can, if they weren't different masses, you can use this equation to compute the center of mass. And the reason why we're using the center of mass, it just makes this equation much easier to deal with. We don't need to involve matrices, and we can just differentiate it. Or, excuse me, yes, solve the differential equation without using a whole bunch of linear algebra. So if we use the center of mass, we can, perform auxiliary polynomial roots to find that r plus I omega and r minus I omega are equal to 0 are the solutions to this homogeneous second order differential equation. Or that's supposed to say sine, so it's supposed to be sine omega t. So but this solution is different than this solution. How come? Am I off the page? Oh, excuse me. So if you missed what I did, this is the auxiliary. These are the auxiliary polynomial roots, and the solution to these is I omega plus and minus I omega w. So then why is this all different? So this can be expressed as, so why is there no imaginary term down here, thanks to Euler's identity? Well, I'll get to that. There technically is, but sign becomes irrelevant because of the two conditions we place on this system. The first condition is that at time initial, at time is equal to 0, the initial displacement is equal to is non-zero. It's equal to the amplitude of the waves. Which makes sense because it's the maximum distance that it will travel in this system. So we can use so just by using that we can solve for C1, and then if we look at the second condition where x prime, or the velocity, is 0 at time 0, which makes sense because at time 0 you immediately release the globes and they haven't started moving yet. So we find that C2 is equal to 0. So we can then express the position function in terms of a cosine function here. Okay, and now for my next example, which is going to be coupled oscillatory motion, which is much more complicated than harmonic oscillatory motion. All right, so if you look at this system, we have 3 springs and 2 different spring constants. So this spring in the middle is a different spring constant than these two. But the masses are identical to make it easy. It's a lot harder when the masses aren't identical. So here I'm taking more of a linear algebra approach to solve this problem with a system of equations. So if we look at our first system of equations, so we said this is equal to m in the x1 direction. So we're going to have negative k x1, which is this right here. And then we're going to have negative k2 plus the displacement caused by this spring and this mass and this mass, which is going to be equal to k2 times x1 minus x2, and then we have the vice versa for m2. And if you think about it, this makes sense. I mean, this represents the term negative k, the negative k1 and the k2, and the x2 here, represented if these masses just oscillated on their own and there was no compression of this spring. But there is going to be compression of this spring, so we're going to need to use a system of equations and a matrix to solve this problem. So if you look here, I just set up a simple matrix where you have x prime, the x double prime, because it's a second order differential equation. I left m here because it's constant and it's easier to solve this matrix, and you can just do it in after. You can just divide over after. Technically, I know you're supposed to multiply it over, but it's just simpler if you don't initially. So yeah, then we have our x1 and x2 values here. So then let's take a look at exactly how we go about solving this. So like it was seen before with our other spring constant equation, we know that the solution to this problem, this other oscillatory problem, has to be something of the similar form, a constant times e to the RT, because that just makes sense. And there's probably an I in there as well. There's probably an I, so we can express this as a sine and cosine function. So doing this, you can just plug this in, x squared into this equation, and then what you'll end up getting is some vector v, two vectors v times mr squared e to the RT. The ERTs will cancel, the v's will cancel, excuse me, and you're just going to be left with a is equal to mrt, and that looks like, excuse me, the v's won't cancel, you need the vectors there. So this ends up being like an eigenfunction here, where you're left with, even though it's only in one dimension, you can approach it as an eigenfunction because it makes solving for a little bit easier. Alright, so you can see the matrix times the vector v is equal to a lambda v, which this is actually just the same as a minus lambda I times v is equal to 0. So all this checks out. And the reason why you don't have m incorporated into the eigenvalues is because it's easier. You can add it back at the end, or you can just pretend the m's not really there. So you'll see later on what the actual correct, I guess, eigenvalue is. But again, I don't want to deal with fractions in my matrix, so I'm just going to do it after. So we go about finding the eigenvalues like you would normally. You know, you take the determinant of a minus the index matrix times the eigenvalues, and you solve, and you're left with lambda. But because you're taking the square root here, this is what I mean. Because you're taking the square root of this term here and the square root of this term here, the m's would just be m. Like the m's squared would go to m, so it's pretty simple to solve, and it just makes it easier to solve without the m. So if you look at this, our eigenvalues are negative k, technically negative k over m, which makes it a little more interesting, and over m here. And what do these two values represent? Well, these two values are the square of the frequency. They're not quite the frequency, but they're the square of the frequency. So if you recall, omega is equal to the square root of the spring constants of the equation over m. So again, r is omega squared, and we find out that once you take the square root, we're left with r1. So I guess is equal to. So I guess our first solution to this, I guess first portion of our solution, excuse me, here is equal to I omega, right? And then here we have another second omega 2, just because the spring constants are up here, we can still express this as an omega. So it's I omega 2. So you're going to have, this is equal to I omega, and then I omega 2. Okay, and now we continue on the back. So like I said here, you find that the solutions are some vector times e I omega 1t, excuse me, plus some other vector times e to the negative I omega t. And these can be expressed as a series of sine and cosine solutions, or series of sine and cosine equations. And these just represent better represent the position of the wave, which makes sense. Again, here you have I sine. These should cancel again, or they shouldn't cancel. They should go to 0, because whenever you start the equation, whenever you start the motion, excuse me, when it's not dampened or nothing like that is involved, the constant term to sine should just be 0. But it's a little different because, well, the oscillation is a complex function, so you kind of need the superposition of i's and cosines to make it work. But anyway, mathematically, for our purposes, it's not going to make that much of a difference. So then we go and we find the eigenvectors. It's pretty standard stuff, you know. And we find the first eigenvector to be 1, 1, and our second to be 1, negative 1. Again, like nothing crazy eigenvector-wise, no imaginary numbers, no rotations. So I guess like the whole point of this is what exactly does omega 1 and omega 2 represent, and what do these eigenvectors and eigenvalues represent? So omega 1 and omega 2 are what's referred as the normal modes of the system. So if we go back and look at our system, if you remember how I talked about if these two were to oscillate, just these two masses, and K were to remain uncompressed or untouched, we would see that the oscillations is very simple. It's harmonic oscillations. It's really easy to figure out, and that's where the first frequency comes from. And the second frequency comes from, as this spring gets compressed, this mass keeps traveling, and then this spring and this spring together compress this mass, this spring, excuse me, twice as much as it would normally be compressed, because it's being compressed by both springs. So these two frequencies are like, wait, what gives? How can a solution in real life have two frequencies? Well, that's just to do with the superposition of waves and frequencies. So it's like the superposition principle. So that's why you can have an extremely complex oscillation. So the oscillation to this isn't very simple. It's a superposition of two frequencies, which makes sense according to linear algebra. So that was an instance where we had to, I guess the math showed one thing, and we had to prove that in real life. So yeah, what do the eigenvalues even represent here? Well, the eigenvalues is the frequency, or the square of the frequency, to make things a little easier, which means it's the resonance. It refers to as the resonance of the natural frequency of the system. So it's just the frequency the system likes to oscillate out, or the normal modes. And then what do these eigenvectors mean? So these are the mode shapes of the vibration. So I'm not 100% sure on what this means, unfortunately, just because, you know, I'm not this far into physics yet. But it has to do with the shape, or I guess like the shape of the sine and cosine functions shown. I mean, in my problems, I'll plot an I'll do like a phase plane of eigenvalues, so I'll get a better idea. But hopefully this gave like some insight onto physics, and I learned a lot of math doing this. I was going to do something with Schrodinger's equation originally, but I mean that's just something I can't handle right now. and it would have taken me a lot longer to explain everything and put together practice problems using that, because I could solve the Schrodinger equation in one dimension, but then why not just use classical mechanics? So I would have to solve it in 3 dimensions, and that's just I'd have to look up a lot of constants because I wouldn't want to spend all day finding them. So it's just a lot simpler to use classical mechanics to model things. And so for my problems, I guess, that I'm turning in, I am talking about a molecule, so an oxygen molecule, which can be modeled by 2 springs, and then I continue with a like a long organic molecule, oleic acid or olive oil, which this group here, this double bond here, can effectively, because there are so many carbons on this side, can be modeled as a spring system with 2 consistent spring, like 2 of the same spring constant here, and 1 different here, and a wall here and a wall here. Just because these atoms are so much smaller than the rest of the molecule, so you can kind of get away with modeling that double bond vibration, or I guess this whole pattern of oscillations, in a similar way to the example I presented. Alright, hopefully you liked what I talked about and learned something. I mean, I certainly did during this project. I learned a lot, and I really enjoyed this class and this project. I spent probably like 6-7 hours yesterday and today just learning physics and learning how to express things, which is pretty difficult when you don't have a teacher to help you with it. But yeah, I really appreciate everything you've done, and maybe I'll go end up at grad school at Penn. I don't really know what I'm going to be doing yet, but yeah, enjoy the rest of your summer.